Hello and welcome to this video where I will take you through the topic number 36 in our book 4, which is electromagnetic induction. Electromagnetic induction. So, as usual, let us start with the specific objectives as they are outlined in our syllabus, because I'd like you to know what you are looking for. Number one, we want to know what is electromagnetic induction. So let's first of all read through the objectives. And here we have it. By the end of this video lecture, you will be able to do the following. You will be able to describe electromagnetic induction. In other words, if somebody were to ask you what is electromagnetic induction, what will you say? You will be able to describe an experiment to demonstrate this phenomenon of electromagnetic induction. You will be able to describe factors affecting the magnitude of the induced EMF. You will be able to state the laws of electromagnetic induction, that is Faraday's law and Lenz's law. You will be able to describe the phenomenon of mutual induction, and you're going to use this phenomenon of mutual induction in describing transformers, because it is applied in transformers. You will be able to describe an alternating current generator. You will be able to describe such a generator. You will be able to describe applications of electromagnetic induction, and lastly, you will be able to solve problems involving transformers. So let's go to the first objective. What is electromagnetic induction? Somewhere when you were in Form 2, you studied the topic magnetic effect of electric current, where you used electricity to create magnetism. And you studied the phenomenon of electromagnets, where you are able to take a soft iron core, wrap an insulated wire around that core, and then you connect a battery across the ends of the wire, and that way you make an electromagnet. We discussed so many things about electromagnets, how to increase their strengths, how to change the polarity of that electromagnet, and we even went ahead and looked at applications of electromagnets. This topic is the opposite of magnetic effect of electric current. In that Form 2 topic, we studied how we come about with magnets when we use electricity. In this topic, we want to see how we will come up with electricity when we use magnets. So it is the other way around. So if somebody asked you what is electromagnetic induction, you will just say it is a production of electricity from magnetism. Now, how would you demonstrate this in a lab? You will need a U magnet, such a magnet. It's called a U magnet because it looks like the letter U. You will need a straight wire, copper wire, and you will need a galvanometer. A galvanometer is a sensitive ammeter with a pointer at the center of the scale. Galvanometers are used to determine the null point in meter bridges. They can also be used to detect small amounts of current or EMF. Remember, in a circuit, in an electric circuit, if we are to tell that a current is flowing, we are going to connect an ammeter in series with whatever load we have. An ammeter. An ammeter is used to measure current, and if it deflects, there is current in that wire. Current cannot flow in a wire unless there is a pump, which is pump in quotes, which is making this current to flow. This agent, which is responsible for determining the direction in which current will flow, or whether there will be current or not, electromotive force or voltage. So if we see that a current is flowing through a wire, then we know one point of the wire is at higher potential, the other one is at a lower electric potential, and it is that potential difference which is making the current to flow. So remember that. If we observe a current in the circuit, it is proof there is EMF in that circuit. So this is a very simple circuit. And one more thing. We know that for us to get voltage, we need a battery. Let us see what happens in this circuit. So this circuit is in 3 dimensions. So I've taken one face of that U magnet and drawn it in 2 dimensions. And then when you look at the wire, the cross section of the wire, it is cylindrical. So this circle here shows the cross section of the wire. If I use this pen here, if I use this pen to represent the wire, when you look at the wire from this perspective, you will see the length of the wire. And that is what we had in the previous slide. There, you'll be able to see the length of the wire. But when I turn the wire like this, so that now you're looking at this cross section here, which is what I have in the next slide here, you'll be able to see the cross section of the pen. So that circle, that blue circle that you can see there, shows the cross section of the wire. Otherwise, its length is in the plane of that paper or that slide. So understand that. So I've not shown the connections to the galvanometer. Rather, what I have here is the blue lines that you can see here. They show the direction of the magnetic field lines. Because this is a magnet, with this side being the North Pole, the N represents North Pole, the S represents South Pole. Magnetic field lines usually point from north to south. That is what the blue arrows mean. The other large arrows, they show in turn the direction in which I'm going to move the wire. This wire, when it is like this, I'm going to move it up. And that is what this first arrow here signifies. You move the wire upwards in such a way that if the magnetic field lines are like this, you can see that when I move it upwards, it is cutting the magnetic field lines. So you either move it upwards as you watch the galvanometer, and then you move it downwards. You move it downwards, you observe the galvanometer, you move to the right, again observing the galvanometer, you move it to the left, and you also move it at an angle. And there are 2 other directions that I've left out here. One of them is that you put the wire and it is stationary in the magnetic field. Again, observe the galvanometer. As opposed to when the wire is moving. The other one is you move it into and out of this plane. Into and out of this plane. It's not possible to demonstrate that. But if you can be able to see what I'm doing, the pen is coming towards you and away from you. Towards you and away from you. And remember, the U magnet is here. And I'm moving it towards you and away from you. We describe that as the wire is moving into and out of the plane of the paper, if such a diagram is drawn on paper. So there are several directions here. If we move that conductor upwards or downwards or at an angle, we will observe that the galvanometer is going to deflect. The galvanometer deflects. Now let's just stop there. when the galvanometer deflects, it is evidence there is a current flowing through that wire. Let's go back to the diagram. When this galvanometer deflects, when the wire is either moved upwards or downwards or at an angle, then it shows that there is a current flowing in this wire. What causes current to flow? Voltage, or electromotive force, EMF. So somehow the movement of the wire has brought about an EMF in the circuit, has created an EMF in the circuit, in quotes. So we are going to conclude one thing, that when the conductor is moved in such a way that it cuts the magnetic field, let me go back to that demonstration and say that when you move it upwards, the galvanometer may deflect to the right, and then it comes back to zero when you're not moving the wire. When you move it downwards, the galvanometer deflects in the opposite direction, and then it comes back to zero. So changing the direction in which you move the wire changes the direction of the current, and that means that the direction of the electromotive force which has been induced in the wire, now it is a time to use that term, induced in the wire. The direction of the induced EMF depends on the direction in which we move that wire. When you move it upwards, it deflects in one direction. When you move it downwards, it deflects in the opposite direction. When you're not moving the wire, there is no deflection, meaning there is no current, there is no induced EMF. When you move it at an angle, it is partly upwards. You can see when you move it at an angle this way, there is a component of that wire which is moving vertically upwards. There is another component which is moving horizontally. Before I go to that, you will observe that when I move the wire to the right or to the left, there is no deflection. So there are two situations here, or three situations where there is no deflection. In fact, 4 situations where there is no deflection. Number 1, when you move the conductor, to the right, there is no deflection, showing no induced EMF. When you move it to the left, no deflection, showing there is no induced EMF. When the wire is stationary in the magnetic field, stationary, it's not moving, there is no induced EMF. And finally, when the wire is moving into and out of the plane of this paper, again there is no induced EMF. So there are situations where the wire is moving and there is induced EMF. There are situations where the wire is moving and there is no induced EMF. So what is the condition that must be fulfilled for there to be EMF induced in the wire? What is the condition that must be fulfilled for an EMF to be induced in the wire? For an EMF to be induced in this wire, first of all, there must be relative motion between the conductor and the magnetic field. There must be relative motion between the conductor and the magnet. Relative motion. And that is not enough. There must be relative motion, and that the conductor must cut the magnetic field. Notice that in a situation where the wire is moving either to the right or to the left, the wire is not cutting any magnetic field lines, although there is a relative motion. So there is no induced EMF, because we've not met that condition. In a situation whereby the conductor is stationary, there is no relative motion and therefore no induced EMF. Again, magnetic field lines are not being cut. But in this first situation where the conductor is moving upwards or downwards or at an angle, magnetic field lines are being cut by the conductor and there is relative motion. First of all, we start by saying there is relative motion between the conductor and the magnet, and that the conductor is cutting the magnetic field lines. When the conductor cuts the magnetic field lines, we say there is magnetic flux linkage. There is magnetic flux linkage. So the condition that must be fulfilled for an EMF to be induced in this conductor is that there must be relative motion between the conductor and the magnet, and that the conductor must cut the magnetic field lines. So that is how we would demonstrate electromagnetic induction. Remember what is electromagnetic induction? A way of coming up with electricity from magnetism. And we can demonstrate it using a U-magnet, a straight wire, and a galvanometer. But when you carry out this experiment in the lab, you must be careful that you use a very strong magnet. This is one of those very strong magnets. If the magnetic is not very strong, you won't notice any deflection there. And then those are the apparatus that you will need to use. And then what do? You move the conductor in different directions, up or downwards, in such a way that the conductor cuts the magnetic field, to the right or to the left, in such a way that the conductor moves but it does not cut any magnetic field, or it remains stationary in the magnetic field, or it moves into and out of the plane of this paper, or finally it moves at an angle. So that is what you do. And you notice that there are situations whereby there is induced EMF. So long as you identify a situation whereby when the conductor moves, you can see that it is moving from one line to the next, then it is cutting the magnetic field lines. You can see here. But when it is moving parallel like that, it's not changing the magnetic field lines that it's cutting, There is no change in magnetic flux. So you end up concluding that for an EMF to be induced in this conductor, there must be a relative motion between the conductor and the magnet, and that the conductor must cut the magnetic field lines. That one is very, very important. Of course, there is no EMF induced if the conductor moves. First of all, there is no EMF induced if the conductor is stationary, or if it moves, but it moves in such a way that it moves parallel to the magnetic field lines, in such a way that it does not cut the magnetic field lines. Remember, the idea of the conductor cutting the magnetic field lines is very important. And there is no way it can cut the magnetic field lines if it doesn't move. But there is a way it can move, but it does not cut the magnetic field lines. So just saying that the conductor moves in the magnetic field is not enough, because it can move but not cut the magnetic field lines. But where it cuts the magnetic field lines, it must have been moving. So the idea of stating that the conductor must cut the magnetic field lines is important. Or simply put, the conductor moves, there must be relative motion between the conductor and the magnet, and that the conductor must cut magnetic field lines. Let's go back and see. So we've been able to describe electromagnetic induction as a way of coming up with electricity when we use magnetism. We've been able to describe a simple experiment that you can be able to do in the lab to demonstrate electromagnetic induction. Now we want to look at factors affecting the magnitude of induced EMF. So we go back to the same diagram here. one of the factors which affect the magnitude of induced EMF, or if we want to increase the amount of deflection, shows that there is more current flowing, and consequently it implies that there was more induced EMF. One of the things we can do is to use a stronger magnet. Use a stronger magnet. This one here. So the strength of the magnet is a factor. How does it affect the induced induced EMF? The stronger the magnet, the more the induced EMF. So the induced EMF is directly proportional to the strength of the magnetic field. So the other factor is the length of the conductor within the magnetic field. Let me just use the same. If the length of the conductor within the magnetic field is from here to here, and then you double that length by maybe making it into a coil, I'm going to demonstrate that one in a moment so that you can be able to see how this happens. So let me say that this is one of the poles of the magnet. The other pole is here. I'm going to draw it in 3 dimensions so that you'll be able to see when I'm talking about the length of the conductor within the magnetic field. So this is what is going to happen. So when I bring the conductor this way, the length of the conductor is from this point when it enters the magnetic field to this point when it leaves the magnetic field. This is the length of the conductor that we are talking about. The induced EMF depends on the length of the conductor within the magnetic field. So I want to increase that length. What I'm going to do, I'm going to go around this pole like this, go around like this, and then I repeat, so that now I seem to have 2 lengths. I have doubled the length. I come back, like that. Tripled the length, like that. And you can see now I have increased the length of the conductor within the magnetic field. Remember, these ones are still connected to the same galvanometer. So factor number 1 was the strength of the magnet. The induced EMF is directly proportional to the strength of the magnetic field, B. We usually use B to represent strength of the magnetic field. The other one is the length of the conductor within the magnetic field. The other one is the speed of the conductor. Move the speed of the conductor up and down at a higher speed. You're going to generate more EMF. And then finally, make sure that the conductor cuts the magnetic field at 90 degrees. Because when it cuts the magnetic field at an angle, there will be less induced EMF. There will be less induced EMF. So here, I'm going just to add this. Do not bother to memorize this. You may memorize the equation because it helps you to remember the factors. Just say BLV cos theta or BLV theta. B is the strength of the magnetic field. L is the length of the conductor within the magnetic field. V is the speed of the conductor. And theta is the angle at which the conductor cuts the magnetic field. There you have it, the 4 factors. BLV cos theta. BLV cos theta. Just remember that. So those are the factors which affect the magnitude of the induced EMF. Let us look at the next objective. So we have just looked at the factors affecting the magnitude of induced EMF. The next one is the laws of electromagnetic induction. The laws of electromagnetic induction, and these are Faraday's law and Lenz's law. Faraday's law and Lenz's law. Faraday's law just describes the factors which affect the magnitude of the induced EMF, because it states that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. At our level, I will leave it at that. But what you are supposed to understand from this is this: that when the magnetic linkage changes, and it changes at a higher rate, there is more induced EMF. That is why we say that the induced EMF is directly proportional. It means that if the rate of change of magnetic flux linkage doubles, then the induced EMF doubles. The other one, which is called the Lenz's law, that is what we are going to spend more time on discussing. But before we look at Lenz's law, I'd like to look at how we determine the direction of the induced EMF. Now again here, I'm going to draw the same U magnet. The diagram may not be so neat like in the slides that I had, but I hope you're going to understand what is happening here. So this is the North Pole and this is the South Pole. And then the conductor is here. Now let's see what happens when we move the conductor upwards. There is something else which I want you to remember. If somebody gives you this symbol, a circle and a dot, and another symbol, a circle and an X, this is what a circle and a dot means. It means that the circle means that you are looking at the cross-sectional area of the conductor. The dot means that the current is coming towards you. The current is coming towards you. Or we can interpret it as current coming out of the paper. The other one means, again, we are looking at the cross-section area of the wire with the current moving away from you or moving into the paper. This more like when you look at the darts. For those who like to play this game, when you look at the flights, when this dart is moving away from you, there's a tip like that. When this dart, when you are here and you're looking at this dart as it moves away from you, then you are looking at the flights. These are the flights, and you will see the flights, and it is an X. But if you're here and you're looking at the dart coming towards you, God forbid, you don't position your eye here and the dart is coming towards you, but let's just imagine that that is the case. The dart is coming towards you. You will see the tip of the dart. So you can use this simple situation to remember what this means. Now, the other thing is this, before we look at that diagram, I'd like you to use your right hand, not left hand. And then I want you to hold the thumb, the first finger, and the second finger in such a way that the three fingers are perpendicular to each other, like this. Like this. You can see when I hold it like this finger and this finger, they are perpendicular to each other. When I hold it like this finger and this finger, they are perpendicular to each other. And when I hold it like this, you can see that this one and this one are perpendicular, and of course this one and this one, they are perpendicular to each other. So hold your first finger, second finger, and thumb in such a way that they are mutually perpendicular to each other. And then you will come to this diagram. I'll come to this diagram, and for me, I'll position myself here and say, that is it, from north to south. This one points in the direction of the magnetic field. And the thumb shows the direction in which the conductor is moving. It's moving upwards. And the second finger shows that current must be into the paper. Into the paper. So current is moving away from me. What have we learned about this symbol here? Current moving away from you. So you'll come here and say, this current here is an X. How about if this conductor is being moved downwards? Again, you will be able to use your, it's called Fleming's right hand rule. Fleming's right hand rule for generators. Remember, somewhere in Form 2, we learned about Fleming's left hand rule for motors. This one is Fleming's right hand rule for generators. So if you're moving it down, of course, the direction here will be a dot. So I can be able to use Fleming's right hand rule to determine the direction of the induced current, in which case I have determined the direction of the induced EMF. So that is how we use Fleming's right hand rule to determine the direction of the induced EMF. And you usually get questions like this in the exam. So in the next video, I'm going to dwell more on this as I look at Lenz's law, because Lenz's law is also very important. So in the next video, don't miss the next video. I'm going to talk about Lenz's law. See you then.